So let's do the following. I'll just do a little exercise. See how you guys fare. This is my sort of J, K, and we'll make this the A flip-flop, which will output A and A prime. And then what we'll do is we'll get another flip-flop JB, KB, and outputs B and B prime. What we're going to do with these two flip-flops is we're going to connect them like that. And then we're going to connect them like that. Alright. Given the two flip-flops in the associated circuit, find the present state, next state machine. Find the draw the finite state machine diagram. Now, how do we approach this problem? Anyone care to volunteer, or shall I call on some people? Kaylee, what do you think we should do here? Well, take a guess. I mean, how shall we start the problem? No idea? Why don't we write down what we know? What do we know? Apparently we don't know much. We must know something. Does anybody know anything about this circuit? Yeah, we see there's wires, and so this says that JA equals B, and then that says KA equals B prime. I mean, this is just what we know from looking, right? We know that JB must equal A prime, and we know KB must equal A. So we know that, right? What do you think we should do next? Our goal is to write a finite state machine diagram. So for that we're going to need something. Anybody know what we might need? Madison, what do you think we need? Yeah, let's start with the present state, next state diagram by creating the truth table. So we'll do the present state, and we'll just write A and B, and then we'll just write out all possible combinations for present state. And now we can continue to write what we know. We know JA and KA, and we know JB and KB. This problem, by the way, is much easier than the problem you're likely to encounter on the final. So I'm starting with a really easy problem. So if I know JA equals B, then I can take B and I can write it out on JA. 0, 1, 0, 1. And I know KA is B prime, so I just invert it. 0, 1, 0. And JB is equal to A prime, so I take A prime, 1, 1, 0, 0. And then I got KB, which is equal to A, and that's 0, 0, 1, 1. Does everybody sort of follow along with me so far? So all I did was I said, oh, there's a wire from JA to B, and so JA equals B, and I copied it. There's a wire from KA to B prime, so I just took KA and inverted B and wrote B prime. So that's it. I mean, that's the whole thing. That's all I did. I just wrote down what's in the diagram. But I'm missing a critical piece, right? I need the next state. So A plus and B plus are the next states. And I have to know something about JK flip-flops, right? So what do I know? I know that JK can have inputs 0, 0, 0, 1, 1, 0, 1, 1, and each of these has a different meaning. This one is the hold, this one's the reset, that's the set, and this is the toggle. Well, it looks like everything here is either reset or set. Reset, set, 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 reset, reset. Well, if it's a reset, the next state is going to be a 0. If it's a set, the next state's going to be a 1. That's all I know. I mean, set it means make it a 1. Reset it means make it a 0. That's what I know. So this is going to be 0, 1, 0, 1. 0, 1, 0, 1. That's it. That's all I know. This one says 1, 1, 0, 0. So I go write that down. 1, 1, 0, 0, because that's all I know. That's all I know. But now I have a present state and I have a next state. I can number this 0, 1, 2, 3, and I can number that 1, 3, 0, 2. And so that says if you're in state 0, next state is 1. If you're in state 1, next state is 3. If you're in state 3, next state is 2. If you're in state 2, next state is 0. So I write down my present state, next state diagram. All I need now is a finite state machine diagram, which says 0 goes to 1. Right? And then it says here 1 goes to 3. And it says here 3 goes to 2. And it says here 2 goes back to 0. Bang, I'm done. I have reverse engineered a twisted ring counter. This here is what the Vice President of Boroughs, Robert Johnson, was talking about. This here is a twisted ring counter. And the interesting thing about this sequence, if you write it out, 0, 0, 0, 1, 1, 1, 1, 0, is it looks just like the top or the side of a K-map, doesn't it? Why? Because we're outputting a gray code. 0, 0, 0, 1, 1, 1, 1, 0. Right? Just like the K-maps. So we were able to do it just by taking these two little guys and crossing the wires, and voila. And the interesting thing here is there's only one bit of difference as we go from one number to the next. And that is a gray code, created by Francis Gray from AT&T Bell Labs. So this is a convenient way to generate rather large gray code sequences with the number of bits equal to the number of JK flip-flops you might like to have. Just keep adding more flip-flops, cross them in only one place, and bang, you're done. You got your gray codes. Is everybody kind of understanding what's going on here? Because I got a feeling that some people were lost last time, and oh gosh, I don't like it when people get lost. So I thought I'd try and pare down the example so that it was really simple. Does everybody follow on this? Who's a little confused? Sure. Yeah. Okay, so we know the input is 1, 0. And we also know that 1, 0 corresponds to J is a 1 and K is a 0. And we know that that's the set state because this goes set, reset. That's the normal equivalent, only with the difference, instead of an SR latch, if they're both 1s, it turns into a toggle flip-flop. But we don't have any cases where they're both 1s or where they're both 0. Oh, wait a minute. No, that's next state. Here it is. So, yeah, had me worried. So as a result, I can see right in through here, that corresponds to a reset. Right in through here, that corresponds to a set. You can see the 2 bits are both set. And here you can see it's going reset, set, 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 right, goes to 1, 1, reset, reset, 0, 0, set, reset, 1, 0. So that's my, oh, I'm getting echo here. Yeah, that's my explanation. Did that make any sense? Okay. Any other questions about how we solve these reverse engineering problems? Would it be helpful if I did one more? Let's do another. I'm just going to make this up. I have no idea what it's going to do. So we'll do this real simple one, J, K, A, and here's A, and here's A prime. And we're going to take A and convert it to K. We'll take A prime and convert it to J. What does it do? I, by the way, don't know. Anybody have any ideas? How do you compute this? What do I do to start? Kristen, what shall I do to start? Yeah, let's do it. So I know JA and I know KA. What do you think that's equal to? There you go. And KA is equal to A. So we're good. And now we have to create our little present state thing with only A as an input, and it can be either 0 or 1. And I can write down JA and KA, and I know that JA is equal to A prime, so that's a 1 and a 0, and KA is equal to 0 and 1. That's what I know. So now A plus and B plus, well, there is no B plus, there's only A plus. That says, well, we're going to set the flip-flop, so it's a 1. That says we're going to reset the flip-flop, so it's a 0. So our present state, next state diagram starts out this way. 0. Next state is going to be a 1. 1. Next state is going to be a 0. And that's what we know. That's our diagram. So all this does is it oscillates between 0 and 1. That's it. Simplest thing. It's a buzzer. It's a buzzer. Any questions about what I did here? Things got a lot simpler when it was just one JK flip-flop. Alright, so now that we're kind of up to speed on how to reverse engineer these things, let's have a look at one of the questions from the test. Alright. Sorry, I'm scrolling. Apparently 41 is like at the bottom or something. Question 41. Okay. So here's Bell Labs researcher Frank Gray introducing the term reflected binary code, which I had alluded to just earlier, remarking that the code has yet no recognized name. The code is now called gray code, and today gray codes are widely used to facilitate error correction in digital communications, terrestrial microwave, and of course in K-maps, and some cable TV systems. The 2-bit gray code is given by, interesting, isn't it? Let's have a look. The 2-bit gray code is given by 00, 01, 11, 10, just like it says here. And here's how you generate the 2-bit gray code for question 41. So then it says here, design a Moore machine. And we know Moore machines are Moore machines because their output is a function only of the state, and in fact that's what happens with this counter. The output's function only of the state. That uses a 3-bit gray code with D flip-flops. Whenever a 111 is visited, the output is a 1, and otherwise the output is a 0. I see what he's saying. Okay. And then the sequence 000, 001, 010, 00010, sorry. 000, 001, 011, 010, 110, 111, 101, 100. What are the correct equations for the flip-flops? Let's start a fresh piece of paper. So it says here, and what we need to do is this is classic. English language description of the problem has to be implemented. Right? Digital designers are not told by their boss how to implement these things. Nobody gives you a lesson, so you got to figure it out. So he says he's going to go, and I'm going to convert the binary into decimal because it's a little easier for me to write. 0, 1, 3, 2, doing this on the fly, 6, 7. And then he says 5, 4, and he goes back to the beginning, and he says whenever a 111 is visited, the output is a 0, so that corresponds to 7. Now the output is a 1. The output is a 1. And otherwise the output is a 0. So I'm going to take the outputs and I'm going to write them right next to the state, because this is going to be a Moore machine and outputs are only a function of state. Now I'll just draw circles around everything, because this is a counter. Visits each state once and only once. It's not even a complex counter because there's no up-down associated with it. And I think this finite state machine captures the problem. That's what we want. So you can see output is a 1 whenever we visit 111. Otherwise it's a 0. And we go through the sequence 0, 1, 3, 2, 6, 7, 5, 4, and then back to the beginning. Okay. How do I approach this problem, everybody? Evan, what should I do first? Well, there's no the states don't have any equality with respect to one another. It's just a counter, so you're not going to try and do state minimization here. We just want to do a straight implementation, it says here. So, I mean, if you did a state minimization without being asked to do it, you would get an answer that wouldn't be in your answer key. So what you need to do is you need to answer only the question that's presented, which is what are the correct equations for the flip-flops, besides which I don't think this would yield to any state minimization at all. So if that's what you were driving at. So yeah, let's skip over that step because that won't be needed. And let's go straight to an implementation. How do I implement this finite state machine, Evan? What do I do? It says use D flip-flops in the directive. It says design a Moore machine that uses 3-bit gray code using D flip-flops, it says. So you have to use D flip-flops. But before you go there, what's my first step? Well, how about we do a present state, next state table? Would that be all right? So we'll do this. Present state, A and B, and C, because we need 3 bits. The next state will be A plus, B plus, and C plus. See? And so what we'll do is we'll just write down all possible No, I can't count. I can't count. There. All possible starting states. And then we'll write out the next state. So after state 0 comes state 1. After state 1 comes state 3. After state 3 comes state 2. After state 2 comes state 6. After state 6 comes state 7. After state 7 comes state 5. After state 5 comes state 4. And after state 4 we reset to 0. And that's what we know. Present state, next state table. And then we have to do our D flip-flops. Because it says D flip-flops. Use D flip-flops. So D sub A, D sub B, D sub C. Evan, what do you think the inputs should be on the D flip-flops? That's it. That's exactly right. So this is our input. And now we wanted equations. Well, what do I do to get equations? What if the equations were in a minimal sum of products form? How would I get a minimal sum of products form from this truth table? Anybody? Yeah, let's do K-maps. I like it. Let's do the K-maps again. So this is A, B, and C. And we'll just write 0, 0, 0, 1, 1, 1, 1, 0. Oops. And we'll do D sub A equals, and now we can write out the truth table. It has a 1 and 2, 5, 6, and 7. Loop here, loop there, and then I can come up with B, C prime, or A, C. Similarly, I got ones in 1, 2, 3, and 6. And D sub B must be equal to C prime B, or C A prime C. And now I can do it again. And I got ones in 0, 1, 6, and 7. And we're off the page. Now let's see. There. It's a little better. So that's A prime, B prime, or AB. And those are your equations. And so then what you do is you want to go and you want to look and see if you can find these equations somewhere. And one of them says D C prime AC. B C prime AC is correct. B C prime A prime C. Yep. Actually, I should put this in alphabetical order, but that's all right. The other one says A prime B prime. That's there. And AB, so that's there. So this is correct, except that was should have been B first. Other than that, makes no difference. It matches exactly with the answer key. And to, well, I don't know if it makes sense to do an implicant chart, because you won't be able to get any reductions from implicant charts. But even if you could, if you did get a reduction from an implicant chart, you wouldn't get the same answers in your answer key. And that wouldn't be good, because then you wouldn't be able to find the answer. How am I doing here so far? Are people confused still by what I've done here today? Who's confused? Please be honest. Now is the time to say something. Is it not clear? Maybe if I scroll down a little bit. Can you see it now? Sure. Yeah, I probably should write it over here or something like that. Any other comments or questions or issues with this example? Who's still confused? Nobody? That's good. That's good. Are there any other questions you'd like me to cover here out of the final? Sure thing. Let's do it. Let's do number 13. Alright, so it says here page 669 shows a diode. Well now, it so happens, oops, I have a book, and I think it says 669, so we can go to that. It's nearly the back of the book, isn't it? 669. I hope you guys have copies of the book. It wasn't a terribly expensive book because we're using the old one, you know. Here it is. Oh, look, it's a diode. See, there it is. Here's the diode. It says here 669 shows a diode. The direction of flow follows the arrow, so it goes that way, from anode to cathode. Forward bias has zero resistance. In theory. In theory. However, in practical implementation, the diode will not have zero resistance in the forward direction. Reverse bias has infinite resistance. In theory. That's the theoretical model. But in reality, it actually doesn't have infinite resistance, and it will have a breakdown voltage, and it won't always work the way you'd expect. And it says here, what kind of voltage drop can you expect in the semiconductor diode? And then it says here, the diode is not a perfect conductor. See, this is not zero resistance. So there is a small voltage drop, approximately 0.7 of a volt. So, gave you the page number. All you had to do was open the book, and you would find the answer right there. Right there. See, it's in the book. Even gave you the page number. What a nice guy I am. So that's a diode. It's a one-way valve for electricity. In the world of plumbing, we call this a check valve. You could put a check valve on a sewer pipe to make sure stuff only goes in one direction and doesn't back up into your house. That's a typical check valve. Goes in one direction only. Sometimes when you look at a check valve, I'm going to write in the book. How's that? Here's a check valve, right? It's a flap that goes sort of on a hinge across the top, and then flow goes in one direction, and it goes right up against sort of another pipe, and so you might have like a little hinge in there. So flow goes in one direction, but it won't go back the other way. Oh, I've screwed it up. Look how I smushed my book. Oh no. So that's a check valve. Flow goes in only one direction, or at least it's resistant to flow going in the reverse direction. Check valve. And then Don't write in your book, because that's bad. Any other questions? Number 1. Let's try that. Draw the state diagram to detect a string of 3 or more consecutive ones in an arbitrary string. Okay. So suppose we start with 0. And, ooh, it's off the screen. And we let 0 be there are no ones. If a 0 comes in, we stay in state 0. But if a 1 comes in, we go to state 1. And our output here is 0, and output here is 0, because we haven't seen 3 1s yet. Now let's assume that we get another 0. So a 0 lets us stay here, a 1 gets us into transition, a 0 has us go back. We got to start again. And let's assume we got 2 1s in a row. Now you're in state 2. But if you get a 0, you go back, you reset. Because you wanted, what's you want? This is question 1. 3 1s in a row. 3 1s in a row. So now let's assume we go to state 2. The output is still 0. Now let's go to state 3. Now the output is a 1. You've gotten your 3rd 1 in a row. Now suppose you get into state 3 and there's a 0. You got to reset, and you got to go all the way back to the beginning. Now let's assume that you are in state 3. You've had 3 1s in a row, but you get another 1. So now you stay in state 3 and output another 1. So this will generally work for 3 1s in a row. So you can look and see if you can find something with 4 states. Doesn't seem to be working. Can't find it. So now what you've got to do is you've got to use the state diagrams that are presented and try and find one that complies with the requirement. So here's an interesting one. It says if you're in state 1, you transition to state 2. So he's not even numbering starting with 0. So let's have a look. Just want to make sure I got this right. Choose the state diagram to detect a string of 3 or more consecutive 1s in an arbitrary string. Okay, so let's try this. If you're in state 0 and you get a 0, you end up in state, oh, he doesn't have state with 0. I'm going to try the one from the bottom. I have to try each one of these things. You know, it's kind of an interesting example because you're presented with a bunch of state diagrams. So this is one of them. Let's see, it goes state 1, state 2, state 3, state 4, state 5, state 6, and state 7. And state 7 gives you a 1. And everybody else appears to be outputting a 0. And if you get a 0 in state 1, you end up in state 2. If you get a 0 in state 2, you stay in state 2. If you get a 0 in state 3, you jump to state 5. If you get a, boy, this is a gobbledygook diagram, isn't it? If you're in state 2 and you get a 0, you stay in state 2. If you're in state 3 and you get a 1, you end up in state 6. If you're in state 3 and you get a 0, you end up in state 5. If you're in state 4 and you get a 0, you go back to state 2. If you're in state 4 and you get a 1, you jump to state 6. If you're in state 5 and you get a 0, you jump to state 2. If you're in state 5 and you get a 1, where do you go? State 3, looks like. Boy, this is complicated. State 6 brings us to state 7. If it gets a 1, state 7 stays in state 7. If it gets a 1, state 7 goes back to state 1. State 1, that's supposed to be state 1. If you get a 0, and I think I've captured it. So, not to put too fine a point on it, but if you were to write this out as a binary tree as shown in the book, S1 can be either a 0 or a 1. S2 and S3 can output either 0 or 1. S4, S5, S6, and S7, 0 and 1. And then, if you get a 1 in S7, you output a 1 and you stay in S7. If you get a 0, you go back. And if you get a 0 from S6, you go back. Get a 0 from S5, you go back. Get a 0 from S4, you can go back. So this is a B tree that'll let you recognize arbitrary strings. If you get a 1, your next step would be, like from here, for example, would be to jump over to S5, and then you, from S5, if you got a 1, it would be as though you had 2 1s in a row, so you would go to S7 and look for another 1. So S5 would jump to S7, is that right? Not quite. Well, let's try and string this along and see what happens. This is an interesting example. So let's get the example 0, 0, 1, 1, 1. So if I try that, 0, 0, 1, 1, 1. That'll output a 1. And it'll keep outputting 1. So that's correct. Let's try another one. 0, 1, 0, 1, 1, 1. So if I have 0, let's see, when you're in state 2 and you get a 1, where do you go? You go to state 4. And for some reason that's not shown here. Well, it should be. If you're in state 2 and you get a 1, you should go to state 4. I think this is not correctly drawn. There we go. So if you're in state 2 and you get a 1, you go to state 4. So that's good. So now let's do that. I got a 0, and then a 1, and then a 0, which resets me back to 2, and then a 1, so I got to state 4, and another 1 gets me to state 6, and then a third 1. Now I'm in state 7 and I output a 1. So let's see if we can run the exercise with the sample bits. There's 1, 2, 3, 4, I don't know how many 1s in a row. Then it says 0, 1, 1, 0. Then it says something like 3 1s or 4 1s in a row. Let's just see how that traces out. So if you get a 1 and you're in state 1, you should go to state 3. It doesn't show that in my diagram because I didn't draw it. That should have been there. I'm trying to redraw what's in the final. So state 1, get a 1, goes to state 3. Get another 1, goes to state 5. Get another 1 from state 5, and it goes back to state 3. Get another 1. Oh, that's interesting. So I have 1, goes to state 3. I want to make sure I drew that right. Another 1 goes from state 3 to state 6. I think I've drawn this wrong. Right? Oh, here it is. That loop is supposed to be the state 6. I'm looking at the diagram and looking at what I drew, and I see it doesn't get better when I redraw it, unfortunately. So you've got to redraw this a little bit neater than I did in order to trace it. So you're in state 1, you get a 1, you end up in state 3. You're in state 3, you get a 1, you go to state 5. You're in state 5, you get a 1, nope, sorry. If you're in state 3 and you get a 1, you go to state 6, it says. You're in state 6, you get a 1, you end up in state 7, so that's correct. You know what you need? The thing to do is to take the present state and next state and write the outputs. If you do that, oh, you need to know the inputs on each of these things. Let's do it again. I'm going to take a little liberty here and just do this the way I think it should be done. Present state, S1, S2, S3, S4, S5, S6, S7. Next state for x equal 0 or x equal 1, and the output is a 1. There. That's better. So if you're in state 1 and you get a 0, next state is S2. If you're in state, this is easier, right? Because you don't have to try and follow through the spaghetti. If you're in state 1 and you get a 1, next state is 3. Outputs are always going to be 0, except in state 7. In state 2, next state is going to be 2, S2, or S4. If you're in state 3, next state is going to be S5, or state 6. Yeah, that's much nicer. If you're in state 4, next state is going to be S2, or S6. If you're in state 5, next state is going to be S2 or S3. If you're in state 6, next state will be S7 or S2. And if you're in state 7, next state will be S1 or S7. And that is the present state next state table as I understand it, unless I've made a mistake. So now let's try and run through the example. And you could do an actual you could do a couple of row reductions on this as if you wanted to do an implicant table. But anyways, the inputs are going to be something like 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1. So let's just try. If you get a 1, it's S3, then goes to, the next one is going to be S6, and then by the third one you'll be in S7, and that ought to be able to, let's just make sure, S6, if you get a 1, should be S7. That should say 7. If you get a 0 from S6, it goes back to S2. So now let's go and take a look at 0, 1, 1. So if you're in S7 and you get a 0, you go back to S1, you get another 1, and that takes you to S3, and another 1 that takes you to S6. But then it says 0, so you go back to S2. Then it says 1, 1, 1, so you get a 1, so that's S4, and then you go to S6, and then you're off to S7, and you're outputting a 1. So that sort of works. Now, what you could do, if you wanted to be sort of cool about it, is you could write S2, S3, S4, S5, S6, S7, and then do your implicant chart. And write S1, S2, S3, S4, S5, S6. And then you could see that S1 is different from S7, S2 is different from S7, S3 is different, S4 is different, S5 is different, and S6, all different from S7. And then you could do your pairwise comparison. Is S1 like S2? And if the answer is yeah, if S3 is like S4, well, we don't know about S3 and S4 unless we know that S2 is like S5, and we don't know that either. Is S2 like S5? Not quite. So there's a few different things we should probably be doing. We could go and run through this. If you do your implicant chart right, you should be able to get a reduction in here. Let's see, where would that be? How about S5 and S6? If S2 equals S2, that's good, and if S3 equals S7. So here's S5 and S6, and it depends on S3 and 7. S3 and 7 we know are out, so that's good. We can get rid of that. Let's look at S4 and S5. And I'm going up the diagonal here. S4 and S5 are equal if S3 equals S6. So I need 3 and 6. Let's look at 3 and 6. I don't know about them, so I'll take a look. 3 and 6 are equal if I get 2 and 5 and 6 and 7. 2 and 5, 6 and 7 are not equal, so 3 and 6 is not equal. Therefore, this is not equal. So now go to the next diagonal, and he says 3 and 4. Let's take a look. So that's 2 and 5, or 6 and 6. So this needs 2, 5. And 2 and 5 are equal if 3 and 4. And 3 and 4 are equal if 2 and 5. So I have 2 is equivalent to 5, and 3 is equivalent to 4. So I've got a circular thing going on. And now I can proceed to the next step up, 2 and 3. 2 and 3 are good if 2 equals 5. We know 2 equals 5, so that's good. And if 6 equals 4, well, we don't know about 6 and 4, so we'll go to 2, 3, and we'll put in 6, 4, and take a look at 6, 4. Here's 6, and there's 4. I don't know anything about it, so let's keep looking. It's true if 6 and 7 are equal, 6, 7. If I take a look at 6, 7, they're not equal. And as a result, 5 is not equal to S6. Let's take a look now. If S2 is equal to S3, if 2 equals 5, let's see, does 2 equal 5? And the answer is yes. And if 6 equals 4, and does 6 equal 4? And the answer is no. So that's good. Got another one out. So we got a couple of equals. We got a few that we've excluded. We can continue. Does S1 equal S2? And then the answer is yes if 3 equals 4. 3 does equal 4, so 1 equals 2. So that's good. And I can write that down. 1 is equivalent to 2. So I'm getting some reductions here. And you knew that you would. So now I can keep going. S3 and S1 is true if 2 is equal to 5. 2 is equal to 5, so that's good. And if 3 is equal to 6. And 3 is not equal to 6, so that's gone. Then we could do S1 and S4. S1, S4 is S3, S6. S3, S6 is out. Now we can do S1, S5. S1, S5 is good if, oh look, they're both well equivalent. So S1 equals S5, that's good. And if that's true, 2 equals 5, so 1 equals 2 equals 5. They're all equal. That's doing a lot of elimination here. So now we do S1 and S6, and we got 2 and 2, and we got 3 and 7. Does 3 equal 7? No, so that's done. And how about 2 and 4? 2 and 4 are equal if we have 4 and 6. 4 and 6 are not equal, so that's done. We got 2 and 6 in here, so we take 2 and 6 and we do a scan, and it says 4 and 7. We take a look at 4 and 7, that's out. And then we look at 3 and 5. 3 and 5 will be true if 2 is equal to 5, and it is. And if 3 is equal to 6, and it is not. So that's done. So now we're left with this. And what we can do is we can cross out 5. We can cross out 2. Anywhere we see 2, we can just write 1. Anywhere we see 5, we can write 1. Anywhere we see 1, let's see, 2 and 5. I think we got them all. And then it says here 4 gets taken out, and anywhere we see 4 we can write 3. I don't even see 4 anywhere, so that's good. And so now our finite state machine diagram has gotten a whole lot smaller. We're down to 1, 2, 3, 4 states, which in fact is how I started to begin with, 4 states. So my diagram as I started, just from my randomness, got me into a minimum number of states. And that's all you really need, is 4 states. So the extra states were removed, and you can then proceed to reduce this diagram so that it looks just like my diagram, I should think. Perhaps the difference would be the state numbers. But basically it says if you're in S1, next state is S1 if you get a 0. Otherwise you go to S3. If you're in S3 and you get a 0, you go back to S1. That makes sense. If you're in S3 and you get a 1, you go to S6. If you're in S6 and you get a 0, you go back to S1. Well, that makes sense. And if you're in S6 and you get a 1, you go to S7. And if you're in S7 and you get a 0, you go back to S1. Otherwise, you stay in S7. And that's perfect, because now you can see you get 3 1s in a row and you output a 1. And otherwise, you output 0. So the implicant chart actually saved you and reduced you to what turned out to be a correct answer. Right? You just renumbered the states. But otherwise, it's the same exact structure as you saw over here initially. So, implicant charts. That was a real good example, actually. I like that example. Because it takes you through the whole process of doing a state reduction. After you've done the design, you say, oh, yeah, that's how you do it. These guys, I don't know what they do. You take the whole thing, you reverse engineer it into a state diagram, take the state diagram, make your implicant chart, reduce the implicant chart, you get yourself a state diagram that obviously solves the problem. So that's pretty cool. What do you think of that? Yeah, that's correct. I think this is what they show in the last one. Yep. Number 40. Number 40. Oops, went too far. Multiple choice string design. Use the implication charts. Okay, let me reread this. Using implication charts, design the minimum state diagram to detect a string of 3 or more consecutive ones in an arbitrary input string. Assume the states are labeled A, B, C, and D. Okay. It's not all that different from what I just did, I think. Let's start this way. A. If you get a 0, next state should be 0, and the output will be 0. That's all right, I guess. If you get a B, next state will be, let's see, if you get a Z, B. If you get a 0, you stay here. But if you get a 1, you leave. If you're in B and you get a 0, you reset. And otherwise, you go to state C, still outputting a 0. If you get a 0 in state C, you want 3 1s in a row, right? 1, 2, then your third one, you're going to go to state D. If you get a 0, you reset, and otherwise you stay in state D. So here we are, 3 1s in a row, output a 1, keep getting 1s, you're going to keep outputting a 1. Now let's use the implication chart and see if we can reduce this. Let's see. A, B, C, D. Let me just go back a second. Yeah, I got that backwards. B, C, D, A, B, C. Right? You start with the second letter, and here you start with the first letter, and with the penultimate letter. And, oh, you know what? We should probably build the present state, next state table while we're sitting around. Present state, next state, x equals 0, x equal 1, output A, B, C, D. If you're in state A, you get a 0, the next state is going to be A, otherwise it's going to be B. If you're in B and you get a 0, you go to A, otherwise you're going to go to C. If you're in C and you get a 0, you go back to A, otherwise you go to D. If you're in D and you get a 0, you go to A, and otherwise you stay in D. Outputs are going to be 0, 0, 1, nope, 0, and 1. That's probably not going to reduce. But one thing we can say is that A is not equal to D, B is not equal to D, and C is not equal to D. B will be equal to C if A equals A and C equals D. We know C doesn't equal D, so that's done. A equals B if B equals C, but B does not equal C, so that's done. And A equals C if B equals D, but B does not equal D, so that's done. So there's no reduction available. This is a minimal form, and it is identical with one of your answers in the answer key. What do you think of that? Does that sort of... Who's confused by this? Any confusions? Any other questions you'd like me to cover? Number 20. Number 20. Let me see. Where did I pass it? Where is number 20? Number 19. Oh my gosh. This is a big finite state machine diagram. Given the state diagram, choose the fully reduced state transition table that belongs to the given state diagram. Use the implication chart approach. Okay. Here's what we're going to do. What number was this? Was this 40? I'm just going to write that down. Let's do a fresh sheet of paper and go to question 20. What we're going to do is we're going to write, first of all, is it a more machine or a Mealy machine, everybody? You're killing me out here. Somebody participate, please. I'll start. Yes, thank you. Thank you. It's a Moore machine because the outputs are only a function of the state. So what we're going to do is we're going to write down the present state, and we're going to list all the possible present states. A, B, C, D, E, is there an E? Yeah, F, G, is there an H? C, D, F, G. Oddly, oh yes, there is an H, I, yeah, okay. A, B, C, D, E, F, G, H, and I are the present states. Next states will be a function of a single input variable which can be valued at 0 or 1. So x equals 0 or x equal 1. And that will be our next state. So I'm going to go straight to an encoding. I'm not going to attempt to redraw this diagram. If you're in state A and you get a 0, next state is going to be A. If you're in state A and you get a 1, next state is going to be B. If you're in state B and you get a 0, next state is C. If you're in state C and you get a 0, next state is F. If you're in state D and next state is 0, you're going to get a C. If you're in state E and next state and you get a 0, next state is going to be I. If you're in state F and you get a 0, next state is H. And for G, if you're in state G and you get a 0, next state is C. If you're in state H and you get a 0, where's state H? Oh, it's all the way up there. You get an F. If you're in state I and you get a 0, you're in state C. Now let's do the x equal 1 part. If you're in state B and you get a 1, you go to E. If If you're in state C and you get a 1, you go to G. If you're in state D and you get a 1, where do you go? A. If you're in state E and you get a 1, you go to G. If you're in state F and you get a 1, you go to I. If you're in state G and you get a 1, looking for state G, oh, you go to F. If you get in state H and you get a 1, you go to B. And if you're in I and you get a 1, where do you go? E. I think I got that right. Keep me honest and check me, please. So then I got to have outputs. It looks like I get a 1 for state A, C, E, H, and F. So it should say A, C, missed one. A, B, C, okay. E, F, G does not have, G is a 0. B is 0. D, 0. I is 0. So I think I have that right. So this should encode the diagram. It's actually easier just to look at the diagram and write this out than to try and redraw the diagram, I think. What's my next step now? Joseph Crowley. I haven't heard from you in a while. What should I do now, Joe? Yeah, let's do it. How do I do that? Oh, you want to do row reduction first. Sure, we can do that. Let's do row reduction. All right. So let's see. I don't see any ABs down there. I don't see any CEs. I don't see any FGs. Don't see any CAs. Don't see any IGs. Don't see any HIs. Don't see any CFs. Don't see any FBs. Don't see any CEs. I can't do any row reduction, Joe. What do I do now? Yeah, implicant table. Yeah, implicant chart. So let's do that. B, C, D, E, F, G, H, I. A, B, C, D, E, F, G, H. So I stopped at the second to the last letter. And then I do my lower triangular matrix. And now I can say that A is not the same as B because the outputs are different. A is not the same as D, and A is not the same as G, and A is not the same as I. B is not the same as C. B is not the same as E. B is not the same as F. B is not the same as H. C is not the same as D, and it's not the same as G, and not the same as I. D is not the same as E, F, or H. E is not the same as G or I. F is not the same as G or I. G is not the same as H, and H is not the same as I. So that's my lower triangular matrix. Let's go up the diagonal and look at EF. So EF will be the same if G equals I and if H equals I. H does not equal I, this gets an X. Let's go down over here. I'm going in an interesting order. I'm going to go on the secondary diagonal. G equals I if F equals E. Does F equal E? Well, now let's see. There's an X there, so it doesn't. How about F and H? F equals H if F equals H and B equals I. B, I don't know about B and I. Let's look up BI. B equals I if, oh, look at this. There was a row reduction after all. B equals I. So that means B is equivalent to I and F is equivalent to H. Very cool. So now let's go and continue this. So question? How am I doing on time? Oh, running out of time. C equals E if F equals I, and it doesn't. B equals D if A equals E. A equals E if A equals I, but it doesn't. So these are both out. And now I can have A and C if A equals F, and if B equals E. No, it doesn't. So now let's go down to the next diagonal, E and H. E equals H if F equals I. It doesn't. D equals G if A equals F. A equals F if A equals H. A equals H if A equals F. Uh-oh. So A equals F if A equals H, and if B equals I. B does equal I. And A will equal H if A equals F, and if B equals B. So guess what? A equals H, which also equals F, and A equals F, which we knew already. So that's cool. Let's look at the last couple. Here's C and F. C equals F if F equals H. It does equal H, so C equals F. Wait, what else do we need? C equals F if F equals H, and if G equals F. G does not equal F, right? So check it out. I go in over here and it says C equals F. So here's F, here's C. I gotta have F equal to H. I got that, that's good. And I also need G equals I. So here's G and I, they're not equal. So C cannot equal F. And we'll go in here and we'll look at D and I. D equals I if C equals C, that's good. And if A equals E, well, it doesn't. C equals H if F equals F, and if B equals G. So this is BG. And B equals G if C equals C, and if E equals F. Does E equal F? No. So that's no good. And so this is no good. Now, did we do D and E? D and G. D equals G if C equals C and A equals F. A does equal F, so D equals G. That's good. That's good. So we have some nice reductions here. G goes away, and everywhere you see a reference to G, you replace it with D. I goes away, and everywhere you see a reference to I, you replace it with B. H goes away, and F goes away, and everywhere you see H and F, you replace it with A. And I guess that's all you'd need to do to get a reduced finite state machine using implicant charts. And let's see if that's in there. So it should say A, B, C, D, E. And I see A, B, C, D, E. Then it should say AC, ACB, AC, ACB. Yep, that's good. Then it should say BE, DAD, BE, DAD. That's good. Then it should say 10101. 10101. Yep, that's correct. Yay, the crowd is wild. And so that is a correct answer. And that's how you get it. Sorry for keeping you. Hope you enjoy the rest of the day. Please bring your questions with you to our next exciting digital design class. And thank you for your attentions. Thank you. Thank you.